Hello, everyone. So this is the third worksheet or chapter 3 worksheet for Chemistry 2A. I'm John Cypress. I'm one of the TAs for the department. Just as a reminder, this is a series where I go through the problems, where hopefully it helps you on your exams. I will say, if you do know how to do all these problems, you will pretty much get 100 on your exams. If you can do all these problems with no issue whatsoever, you're basically going to get near 100 on your exam. So I highly recommend knowing how to do these problems. All right, so let's start. The first one, it says rubidium has two common isotopes, rubidium 85 and rubidium 87. If the abundance, oh, and how am I reading this? So that's the element. This is the mass of the element. So rubidium 85 and rubidium 87, if the abundance of rubidium 85 is 72.2% and the abundance of rubidium 87 is 27.8%, what is the average of the atomic mass of rubidium? All right. So one thing to note, just very quickly, this is rubidium with different number of neutrons. So these are isotopes of your rubidium. You can't have an element with different numbers of protons because that's a different element, right? So it has a different atomic number, it has a different number of protons. So you can have, if you have isotopes, they only have different numbers of neutrons, but they have the same number of protons. All right, so what is the average atomic mass of rubidium? Well, we have the weight of rubidium, and just to confirm it, right, we have something around 85 and 87 there. We'll talk about it. But how do you do this? So what you do is all you're doing is taking a weighted average. So if you haven't seen that before, or if you've taken something like AP Stats in high school, it's something like this. So the formula is this. You don't have to know this. Um, but that's the formula. So it's essentially weighted by each data point. So xi, the subscripts are just labels. So you have one data point or another data point or other things. You have some data point, you weight it by some sort of thing. In this case, you're weighting it by percent or percent of 100, right? And then you're dividing by the total weight, right, that you're kind of weighing by. So in this case, actually, I'll leave it just in case anyone wants to see it. But all you have to do is this. You take the weight, you take the atomic mass, 85. Then you multiply it by the percent abundance as a decimal. So you're converting from the abundance to a decimal, and then you just add them up. For anyone who hasn't seen this or needs a quick refresher, that just means summing. These little E symbols, you're adding a whole bunch of things together, or every term together. So you add that with 87. So you take the atomic mass and then you convert to a decimal 278. And then you just plug in your calculator and you're done. So I'm actually not going to do that. I'm going to look at the periodic table and that should be our answer, 85.47. So on the periodic table, all of these masses are the weighted averages by percent abundance of the different elements on the periodic table. So rubidium is not actually like any one rubidium. It's not 85.47. It's really a bunch of 85s and then some 87s, and you're averaging the mass, right? So any one rubidium will not have, a fractional weight or a decimal weight. All right, so just something I want to note, right? If you wanted to go by this formula, you don't have to. All you have to do is remember how to do this. Really be dividing by 1 because you're adding a bunch of decimals that add up to 1. If you want to keep everything in terms of percents, that's also okay. You add them all up and you should get 100%. Either way works. I recommend doing the decimal because oftentimes people forget to divide by 100% if they do not. All right, 2. It says titanium has 5 common isotopes of that. What is the average atomic mass? So we're just going to do the same thing. Exactly the same thing. So I'm going to take 46 multiplied by 0.08 plus 47 times 0.078. Also note these decimals, right? Make sure you're converting correctly. 0.8% is 0.08, not 0.8. 0.8 is 80%. You will get it wrong if you do that. 48 times 0.734. My gosh, so many. But you can see the procedure is exactly the same. It's really not too hard. And then I assume the one on the periodic table is the same. So when you plug this into your calculator, you should end up getting 47.9 atomic mass units or grams per mole or whatever. All right. 3. How many moles are present? All right. So one thing I do want to note is what is a mole? Okay. So to start this conversation off, let me label this. Let's start with the analogy of a dozen of eggs. Well, 1 dozen is equal to 12 of something, right? So if you have a dozen eggs, you have 12 eggs. That's what it is. You have 2 dozen eggs, you have 24 eggs, right? Now, a mole of something, it's really the same idea. 1 mole of something, instead of it being 12 of whatever it is, it's 6.022 times 10 to the 23rd of something. So an Avogadro amount of something. That's all it is. That's all it is. It's not more complicated than that. There's always a lot of confusion on it. All a mole is a unit of counting, just like a dozen, just like a half dozen, just like a couple. Right? Couple is 2, half dozen 6, dozen is 12, a mole is 6.022 times 10 to the 23rd. That's all it is. All right. Number 3, it says how many moles are present in 34 grams of copper hydroxide. So this is going to be a unit conversion. Now, something I do want to note is I'm going to put it on, I'm going to put it over here. So when you're converting between units, I usually draw this helpful, at least in my mind, helpful diagram, which may help you figure out how to convert between things. So 3 of the most common things that you'll be seeing, which will be on your test, I promise, is going to be conversions between grams and moles and number of stuff. So usually it's number of atoms or molecules. Now to convert between each of these, there's something that relates them. So you can actually think about it in terms of an equation, which I will write out. I like using the equation way. I know most people just do big fractional multiplication. You either way works. So I just want to make it clear where these things are coming from. So in case you do forget, if you're doing the fraction way of unit conversion, you have something to refer to in your head so you know what to use to convert between the two. So to go from grams to moles, the thing that relates the two that you usually know is molar mass, right? Sometimes you are going to solve for molar mass of something, but generally you have it. And you're going to convert between the two, grams and moles, with the molar mass of something. So the weight on the periodic table, or mass on the periodic table, not weight. Then to convert between moles and number of atoms or molecules using Avogadro's number, right? Because just like a dozen, how do you go from 1 dozen to how many of whatever you have? You multiply by 12, right? That's all it is. For going from moles, number of things, you multiply by Avogadro's number, which is just how many things are in a mole, just like how many things are in a dozen, which is 12. So the formulas that relate all of these quantities, if you like formula methods more to convert, I used to really like formula methods a lot, and they helped me. So I'm going to show you here. So that's the first one. And then this is the second one. You can just use algebra on these, right? So if you wanted to, so if you're looking at the first equation, right, how would you use this? Grams is equal to moles times molecular weight. If you want to solve for moles of something and you have the grams, you can just divide both sides by molar mass, just algebra, right? And then you get moles is equal to grams divided by molar mass, right? Which is what you're doing in the unit conversion as well, except you're kind of doing it in a way you're crossing things off. This way you're doing it with an equation, or to me, at least, it makes more sense it's more clear cut of where to go using algebra. Right. And then the next one is number of atoms or molecules is equal to moles times Avogadro's number, or 6.022 times 10 to the 23rd. Same thing. You can just use some algebra. So let's say if you had moles of something and you wanted to figure out how many atoms or molecules, Avogadro's number is a constant. So that means you always have it. So you just multiply it. You're done. If you have number of something and you want to go to moles, you divide by Avogadro's number. Just like dozen of eggs. Again, use the analogy. Think about that if you're still struggling with that. So you have 24 eggs. How many dozens of eggs do you have? You divide by 12, right? So you get 2 dozen. Same idea here. All right. So now that we have that, it says how many moles are present in 34 grams of copper hydroxide? I'm going to stick with the fraction unit conversion. You can use the equation. That's what I did for many, many years. I'm just going to keep it with the fractions. It looks cleaner. And then I think that's just what people are used to. But do keep these formulas in mind if you get stuck. So we start with 34 grams of copper hydroxide. Now, I do want to note grams is a mass unit, and it should be on the top of your fraction if you're going to convert to moles. Something that you kind of just take for granted, you just put everything on top, but do just keep in mind where your units are going to end up at the end when you're converting. So if you're going from grams to moles, grams will be on the top of the fraction. Same as if you're going the other way around, right? You don't want 1 over grams, or you'll end up with 1 over moles. So we use the molar mass, right? If you want to use these equations, right, or these relations in your head, you're going to use the molar mass, right? If you forget. So the molar mass of copper hydroxide, you would look at the periodic table, you would go ahead and add them all up. I'm not going to do that for the sake of time. So the mass of copper hydroxide is 97.561 grams of copper hydroxide. Now do note how I'm writing out grams of copper hydroxide, not just grams every time. It'll make more sense when we get to stoichiometry. I highly recommend you do this. Otherwise, you will mix things up in the future and make mistakes. So please keep track of just whatever you're converting. So we have this for every 1 mole of copper hydroxide. The grams cancel out, right? And then you go ahead and plug this into your calculator. And so when you plug this all into your calculator, you should get 0.35 moles of copper hydroxide. 4 says how many, and that's it, done. 4 says how many grams are there in that many molecules of NH3. Now, something I actually want to add to this little diagram here is how do you convert between grams and number of atoms or molecules? Right, because you may be wondering, well, I put arrows between grams, moles, and number of molecules. How do you convert between those two? The answer is you can't, not directly. So there is no way for you to go straight from grams to number of something to number of something to grams, right? So you have to convert to moles first. So again, this is where the diagram can be helpful. So the plan of attack is going to be go from number of molecules to the number of moles, the number of grams. So number of molecules, 3.4 times 10 to the 24 molecules of NH3 all over 1. And then we're going to use Avogadro's number to convert between the two. Again, you can use the formula that I wrote above in blue, or you can use this fractional weight. They are mathematically the same. It's just a matter of how you're setting it up and solving for things step by step. So the number of, there are 6.022 times 10 to the 23rd Avogadro's number molecules of NH3 for every 1 mole of NH3. And then, let's see, moles, grams. So now we're going to go from moles to grams, right? So we're going to use the molar mass. The molar mass of NH3 is, I think it's like about 17 or something, or no, 15. No, it's 17. I was right. So it's 17. You have 17 grams of NH3 for 1 mole. And again, if you're using this kind of fractional method, you're trying to cancel out the units, get the unit you want on top. If you're using the equation method, it's actually much more straightforward. You're just plugging into this one, then you plug into that to get grams. Once you go ahead and plug this all in, the answer should end up being 96 grams of NH3, and then you're done. All right, moving on to the next one. It says, how many molecules are there in 24 grams of iron 3 fluoride? So we're just doing the same thing that we just did the last problem, except backwards, right? So we're going to go from grams to moles to number of atoms or molecules. All right. So how many molecules are there? There are 24 grams that we start with. We're going to convert to moles first because we have to. Not allowed to go directly from grams to number of something. So there are the molar mass of iron fluoride. Again, on the test, you would actually do this yourself and add everything up on the periodic table. I don't want to do that. That takes too long, so I'm not going to. And it doesn't really help for you to sit here and watch me add things up. So my calculator. We have 112.84 gram. Oh, that should be on the bottom, right? Because the units need to cancel. 112.84 grams of iron fluoride for every 1 mole of iron fluoride. The grams cancel out. Now we have to go from moles to number of something. So we're going to use Avogadro's number. For every 1 mole of iron we have at 6.022 times 10 to the 23rd molecules of iron fluoride. And then when you plug this all into your calculator, you should get 1.3 times 10 to the 23rd molecules of iron fluoride. 6 says, how many chloride ions are in 200 grams of carbon tetrachloride? So this one's a little bit harder. So how do you do this? Well, first, let's figure out how many molecules of carbon we have. Or, sorry, carbon tetrachloride, okay? So a chloride ion, just as a reminder, is Cl minus, right? Or you can just think of as Cl in this case. A chloride ion is Cl minus, but in this case, you can think about it as either or because you don't see the explicit minus. to make it less confusing. So how many chloride ions are there in 200 grams? Well, first let's figure out how many molecules of carbon tetrachloride we have. Right? Why? Because from that, I can figure out how many chloride ions I have, because I have a certain amount of chlorines in every single molecule of this. So we're doing the same thing. We're doing the same thing, right? We're going from grams to number of molecules first. So first we go from grams to molar mass, or convert using molar mass with to go to moles. Um, I don't know what it is. I think it's like 80, no, 100 something. Yeah, 153.82. Yeah, I was way off. Okay, in my head. So 153.82 grams of carbon tetrachloride for every 1 mole of carbon tetrachloride. Then, so the grams cancel out. So now we use Avogadro's number to go to number of molecules. Again, you can use the equations too. It doesn't matter. Just do keep in mind your units. So I'm writing them all down. The moles cancel out. Then what do we do? Right. So if you look at this molecule, well, there's 4 chlorines or 4 chlorides for every 1 molecule, right? So for every 1 molecule of carbon tetrachloride, we have 4 chloride ions. Then the molecules unit cancels out. Molecules of carbon tetrachloride. Again, this is where it's good to keep track of your units, because now we're not using the same thing, right? We're using CCl4 and Cl minus. So it's easy to get those mixed up, especially when you have harder or longer problems. Once you plug this all in, you should get 3.132 times 10 to the 24th Cl minus ions. You can also convert at the moles level. That's also appropriate. So you can convert from 1 mole of carbon tetrachloride to 4 moles of uh, chloride ions. That also makes sense, right? Because again, a mole is just a conversion factor, right? Just like dozen is. So if you convert at the moles level, I think that's what Dr. Chamberlain may do. That's also okay. Either way works out, and they work out mathematically the same and actually conceptually the same too. Um, I just like to break it all the way down. All right, going down to the next one. It says, what is the empirical formula of a molecule containing these things? All right. So this is something that students struggle with a lot. I recommend that you do get to know these problems in case it comes up on a test. They are not that hard once you know how to do them, but you need to know how to do them, right? So what is the empirical formula? So there's 2 different types of formulas, just to kind of recap. Empirical formula is the smallest ratio of atoms to one another in a compound. So kind of like 4/6 simplifies to 2/3 as a fraction. So if you had something like this, C2H4, the empirical formula is CH2. That's all it is. So it's the simplified ratio of everything to one another. So how do you do it? Well, first you have these percents. This is what you're given. These are percent mass, by the way. So that is important to know, just to make it more clear. Let's just say percent. What happened? My thing does not lasso anymore. Percent by mass. So what you want to do, right? This is again percent by mass. So consider 100 grams of your molecule, right? So these are all in one molecule, and these are the percent masses. Consider 100 grams of the molecule. Why? Because it makes your life easy. You could use whatever you want, right? You could use 27.34. But the reason I'm using 100 is because these are all in percents. So this will make all of the math easier. You can use whatever you want and use the same methods. Um, I highly recommend 100. There's no other reason. There's no reason not to. So this just makes the math easy if you do it out of 100 because percent's out of 100. So out of 100 grams, you have 65.5 grams of carbon because it's 65.5% carbon. You have 5.5 grams of hydrogen. And I'm actually going to leave some more space here. 5.5 grams of hydrogen. And then you have 29 grams of oxygen. Right? Again, you can use whatever you want. I recommend 100. Otherwise, you're going to have to convert these to decimals, multiply them. Just make your life easy. Just do 100. Then what you want to do is convert the moles. Why are we doing this? So you want to convert to moles because mass doesn't really help you relate how much of one thing you have to another thing, because they're different elements, right? Different elements come in different sizes and I guess shapes. So shapes and sizes. And to compare how much you have of one to the other in terms of quantity, so just counting wise, you have to convert to moles, right? It's like if I were to show you this textbook versus this textbook, there's one textbook each, right? However, this one is much bigger than the other one, but there's still one textbook each, right? So if you want to count things, you can't do it in terms of mass. You have to do it in terms of moles, right? If you want to compare how much you have of each. All right. So you convert these to moles. I'm not going to write it out because quite frankly, there's just not enough space for me to keep this clean and do that, do all the conversions. So if you convert these all to moles, right, all you're doing is dividing by the molar mass. I won't show the work for that. I'm saying it right now. The mass of carbon is 12. So if you divide that by 12, it's about 12. You get 5.4, let's just do 6 to 2 decimals, moles of carbon. Then you have 5.5 moles of hydrogen. And then oxygen, you divide by 16 and you get 1.81 moles of oxygen. Great. So now we can compare these things. So what this is saying, what we've gotten so far, is for every 5.46 moles of carbon, I have 5.5 moles of hydrogen, and I have 1.81 moles of oxygen. Now, that's not really helpful when you're talking, right? No one wants to talk like that. It's like I have 1.81 moles of oxygen. It doesn't really make sense. So to make this sound better, and also so we can put it into a formula, what do? What you're going to do is divide by the smallest mole. And this will simplify the ratio, right? If I gave you a ratio like this, 2 to 4 to 6, you can simplify this ratio by dividing everything by 2 and getting 1 to 2 to 3, right? It means the same thing. So we're dividing by the smallest one here, which is oxygen. So O in here, or O in problem. So you're dividing by 1.81, 1.81, 1.81, and then you get some numbers. So 5.46, and these are going to be approximate numbers. This is about equal to 3.02. And the arrows, the reason I'm just indicating it is because I'm also writing what you're doing from step to step. I won't do that for the next one. So you can just write divided by on a test or something. So there's 3.02. You're going to round to the nearest whole number. So about 3.0. Then for hydrogen, it's about the same, right? They're about the same number. And then for oxygen, you get one, of course, because you're dividing by the same thing. Now, if you do keep in mind your units, this will make sense what we're about to do. Right? If you keep in mind your units, this top one is moles of carbon for every 1 mole of oxygen, if you keep your units. The next one is moles of hydrogen for every 1 mole of oxygen. Then the last one is just 1. So because you divide by moles of oxygen. There's 1 mole of oxygen for 1 mole of oxygen, right? So I mean that makes sense. So if you keep those units in mind, right, why can that be helpful? I'm going to delete them to make it a little cleaner. It can be helpful because when we write the formula, that's what we're doing, right? We're comparing the moles of carbon and moles of hydrogen and relating it to the moles of oxygen. So our formula is for every 1 oxygen, I have 3 carbons and 3 hydrogens. For every 1 mole of oxygen, I have 3 carbons, 3 moles of carbon, and 3 moles of hydrogen. And this is your empirical formula. And then that's it. So for these, it's the same process always. For the next one, we're going to do the exact same thing. There's one extra step for the molecular formula, but otherwise it's exactly the same. All right. So going on to number 8, it says, what is the empirical formula of a molecule containing 18.7% lithium, 16.3% carbon, 65% oxygen? And then it tells you the molar mass of a compound. Okay. So keep in mind, the empirical formula is the most simplified ratio. The molecular formula is the actual ratio, right? Like if I told you you had 2 chocolate chip cookies to 4 oatmeal cookies, actually, let me go back on that. Let's say you have 2 chocolate chip cookies and 4 oatmeal cookies, right? The simplified ratio is 1 to 2. For every 1 chocolate chip cookie, you have 2 oatmeal cookies. But the real ratio, what you actually have in terms of cookies, is 2 chocolate chip cookies to 4 oatmeal cookies, right? So empirical is the simplified ratio. Molecular formula is just actually what you have. So we'll figure that out at the end. Sort that out. First part is exactly the same. 18.7 grams of lithium. 16.3 grams of carbon. 65 grams of oxygen, because these are all out of 100 grams, right? Then you go ahead and convert these to moles. Divide by the molar mass. Lithium has a molar mass of 6.941. What was it? 18.7. So 18.7 divided by 6.941. That's 2.0. I'm just going to leave it like that. Moles of lithium out of 100 grams. Carbon, you're doing the same thing. 16.3 divided by 12, 1.36. Then you have oxygen. So 65 divided by 16, 15.999, close enough. 4.06 moles of oxygen. All right, great. So now we have these moles. Then what I'm going to do is divide everything by the smallest one, right? So I can properly compare them in a simplified ratio. So carbon is the smallest, so I'm going to divide by 1.36 for all of them. Then you're going to get about 2 for lithium. For carbon, of course, you get 1 divided by the same number. For carbon, should be, or oxygen, sorry, I think it's about 4. Bad mental math. All right. That is 3.4. So this is not close enough for me to just round. So now we have to remedy this as well. So what do we do? Actually, I was wrong. Plugged it back in. I said 0.6, and I thought that was a 6 when I plugged it in. So be careful when you plug in stuff like that. Mistakes happen, as you just saw. So that's about 3. So the empirical formula is going to be 2 lithiums, a carbon, and 3 oxygens. Now we're not done because it's asking for the molecular formula, right? So how do you do this? Well, first we can find the weight, or I shouldn't say weight. Weight is not technically correct. We can find the molar mass. Of our compound. So the empirical molar mass, right? If you just add these up on the periodic table, so this is the next step that you have to do. You'll see why. Let's see. Lithium is 6.941 plus carbon, which is 12, plus 3 oxygens, which is 48. 3 times 16. So it's 66.94. Oh, no, that's not right. I forgot to add 2 lithiums. Make sure you don't mess that up. 73. There we go. That makes more sense. 73.882 grams per mole. Now what you can do is you can look at the molecular formula, molar mass, and say, well, let's compare the two, right? Let's see how much more the molecular molar mass is than the empirical molar mass, right? So how do you do that? You divide. So 147.6 divided by 73.82. I'm not writing in units because I'm out of space, and just to keep it clean, actually, I'll write it in. I can make them tiny. There. This is about 2. So what does this mean? This indicates that your molecular formula is 2 times the molar mass of your empirical. So to finish this off, all we have to do now is take our empirical formula, and because we know it's 2 times as big, I guess you could say, it has 2 times as much mass as the empirical formula. We're just going to double everything. C2O6. And then you're done. Double it, and that's it. All right. So going on to the next one, number 9. It says we have copper 2 hydroxide. Wait, what are we doing? Oh, percent copper, percent oxygen, so on and so forth. So this is again percent by mass, right? Not by mole, right? If you're doing percent by mole, copper is 1/3, right? There's 3 things. So 1/3 is copper, 2/3 is hydroxide. Um, or 1/3 is copper, uh, 1/3 is oxygen, 1/3 is hydrogen in terms of moles. But we don't want this in moles. These are again going to be percent by mass. So first you have to go ahead and again, I would consider, actually, do we consider 100 grams? Hmm, yeah. So we're going to consider 100 grams of substance again. But how do you do this? There's actually, you don't have to. So the way you do this is all you're going to do is take the molar mass of each component and then divide it by the total. So the total molar mass, or the molar mass of this compound, and you could plug into multiply by 100 grams. It's not going to be helpful though. So the total molar mass of this, let's see, is, again, you would add it up on the periodic table. I'm not. 97.561. So the percent of the total molar mass attributed from copper, and again, we're talking in terms of molar mass now. So if we go back about a minute ago, if you're talking in terms of moles of just the atoms, this doesn't work. But this is by molar mass, right? They're inherently 2 different things. So molar mass is tied to grams, which is why you actually don't have to go to convert to grams or anything else to figure out percent by mass. You can just keep everything in terms of molar mass. And again, it's because of how they're related. So molar mass is related to mass, which is why we can just take this percent, which we're going to do in a sec. So the percent by copper, all you have to do is take the molar mass of copper, 63.55, and divide it by the total. So just a typical percent thing. Then you do times it by 100, and then you get 65.1. You do the same with oxygen. Oxygen, there's 2 of them. It's about 30, 32. 97.561 times 100. So you're just taking, again, a percent of the molar mass here. So it's really not too hard. 32.8%. And then you have percent by hydrogen, which is going to be 2, about 2, divided by that times 100%. And then you get 2.1. And then that's it for this problem. All right, moving on. Whoa, my thing disappeared. There. Moving on to number 10, this is exactly the same thing. So total molar mass. Um, you would add this up on the periodic table. This is, so SO4 is a 2 minus. That means this is a nickel 3. Nickel 3 sulfate. There. 405.58 grams per mole. Then you're going to do the same thing. So you're just going to go ahead and divide each one by the total, right? So nickel, there's 2 nickels. Nickel weighs, it's in the middle, 58.7. There's 2 of them. You divide by the total here. So something I probably should have written explicitly, I apologize that I did not, is for oxygen and for hydrogen. I just took the molecular weight and multiplied it by how many there was, or the molar mass. Molecular weight, molar mass, I kind of use them, we use them interchangeably. They're really technically not the same, but they're used for very much the same things. So yeah, we have this times 100%. And then you should get an answer of 28.9 for the percent of sulfur. You're doing the same thing. Sulfur weighs 32. There's 3 of them, right? Because this is SO4. Each SO4 has 1 sulfur, and there's 3 of them. Over 405. I'm going to delete the units to make this cleaner. 0.58 times 100. And then you get 23.7%. Last but not least, you're doing oxygen. It's the same thing. So if you're already comfortable with this, I recommend you skip this part. There are 12 oxygens. There's 4 in an SO4. And there's 3 of them. 4 times 3 is 12. And then you get 47.3%. And then you're done. All right, moving on. Almost, not almost done. All right, moving on. A compound with an empirical formula of C2H8N and a molar mass of 46 grams per mole. All right. It says write the molecular formula. Oh, so we're just doing what we did for the last part up here, where you have the empirical formula molar mass. You have the molecular formula molar mass, and then you just divide and then multiply. So the molar mass of C2H8N is 2432 plus N, 14. So about 46. Grams per mole. And then the molecular, so if we take the ratio first, right? The molecular is 46 grams per mole. The empirical formula is 46 grams per mole. Now you get 1. What does that mean? Right? Before we got 2. 2 meant that the molecular formula had twice as many things of the same things that we had in the empirical formula. Well, this is 1. So that means the molecular formula is equal to the empirical formula. And the answer is C2H8N. Done. 12, a compound with the empirical formula of that and a molar mass of that. CF bro. So the molar mass of CF bro is 254.7. So it's the same problem. They're the same. They are the same again. So your answer is just CF bro again. Same formula. So your molecular formula can be your empirical formula. 13 says determine the percent of H2O in the hydrate, chromium nitrate with 9 waters, hydrate with 9 waters. So this, you're doing the same thing, right? These are all the same types of problems, right? These are all percent by mass problems, 9 and 10. You're doing the same thing for this other one. So yeah, same exact thing. So the molar mass of chromium nitrate hydrate is let's see. This one we may have to actually we do. So chromium 3 nitrate has a molar mass of 238.011. So that's the first part. 238.011. There's 9 waters. Each water has a weight of about 18. And then we just add them up. So I did 9 times 18. I mean, that's the fastest way to do it. You could add 18 9 separate times. I would not recommend it. So that is the molar mass, 400.011 grams per mole. And then you can find percent by water, taking the contribution from water, which is 9 times 18, divided by the total. And then your answer should end up being 40.5. That's it. Same problem again as we saw before. Um, so this up here is the contribution due to water, right? To the molar mass. Yeah. And then it's the same thing with the other ones. All right. 14, it says the food flavor enhancer monosodium glutamate, MSG, has this composition. What is the empirical formula? So this is the exact same type of problem. Um, yeah, so I will work through this. If you're comfortable with these problems, I highly recommend just going to the next one. We're doing the same thing. So there's 100 grams of the substance. You have 13.6 grams of sodium. You have 35.5 grams of carbon, 4.8 grams of hydrogen, 8.3 grams of nitrogen, right? And also I recommend, as if you've gotten to this point in the video, for those of you that may be here, I recommend that once I do a problem, one type of problem, if it comes up again, do it yourself before you see me do it. Um, Otherwise, you're just losing out on the practice, right? So these videos are supposed to be a supplement, not supposed to be a replacement for you practicing them. Um, then there's 37.8 grams of oxygen. I promise if you don't practice it, you're going to forget it on the test. Um, it's easy to remember a general idea of what to do and not actually remember what to do, right? If I asked you to draw an ace of spades right now, you would probably get the main features right, but you probably would not get the entire card correct. I know I wouldn't. So you get the idea right, but not the details, and you need to know the details. So again, you convert to moles for all of these. So sodium, you have 13 divided by 22.99, 0.57 about. 35.5 divided by 12, 2.96. You have 4.8 divided by 1, which is 4.8. You have 8.3 divided by 14, which is about 0.59. You have 37.8 divided by 16. Then you divide by the smallest. The smallest one here is nitrogen. Nope, is sodium. So sodium is 1. 2.96 divided by that. It's about 5. For that one. Okay. So this one is a little bit tricky because this is 8.42. Now, you're not supposed to round if it's somewhere in the middle, right? These numbers should be pretty close to a whole number, but they shouldn't be that far. So like plus or minus point two is kind of pushing it, but about 0.2, I think you'll be fine. So like if it's 2.2, you can round down, or 1.8, you can round up. But this is 8.42. That's almost exactly in the middle. So we're not gonna round this. So let's do the rest, and then we'll talk about it. Um, mm, no, I don't think they're actually gonna. So actually, round down. That's what they do in the answer key as well. So round down here. Typically, if it's around the middle, you do not round down. Usually, you have to multiply by some positive integer to make it so that it's a whole number. So like multiply by 2 or something. Usually it'll be more clear. I think it was probably just a small mistake in terms of percent compositions or something, um, or excessive rounding. So there's probably just a small thing when writing. Then we have, yeah, it'll be clear on the test, I assume. So for 0.59, this is about 1. Then for 2.36, it's 4.1. Which just goes to about 4. Done. Then you can just write these all together. For the empirical formula, it's going to be NaC5H8NO4. Done. So same as the ones we saw before. Again, I think you'll be fine rounding up or down on the test. It should be just very clear. It's not always the case, though, if you take future classes. So like spectroscopy and OChem. 15, it says the element X forms XCl4 containing 75% chlorine by mass. What is element X? So again, we're doing the contribution thing that we did like for 13 and 9 and 10, except going backwards, right? So we're trying to figure out what is the molar mass of element X first. That's what we want to figure out. So we know that it's 75% chlorine by mass, right? So chlorine, what we can say is chlorine, 4 chlorines, because there's 4 of them. So 4 times 35.5 divided by the molar mass of XCl4. So this is what we just saw up here, right? Contribution divided by the total is equal to 75%. Right. Then we can solve for the molar mass, right? That's fairly straightforward. You do a little bit of algebra, right? Multiply up, then, oh, and I totally forgot, times 100%. I forgot it up here too. Oh no. So multiply by the 100%. Don't forget that. That will mess up your algebra. So you get the molar mass, right? Multiply up, divide by 0.75 or 75%. Yeah. When you do that, let's see what you get. 4 times 35.5 divided by 75 times 100. 189.33. Okay. Now what we can do is figure out what the molar mass of X is, right? So X contributes 25% of this because there's two things. There's X and Cl4. So 25% of this thing is 47.33. And then we get to look at the periodic table. So what has a molar mass of 47.33? The closest one that I see is titanium, 47 at 47.9. So let's go with titanium. And that should be your answer. All right. Moving on to number 16. A 4.05 gram sample of this compound containing only these things was burned completely. The only combustion products were 10.942 grams of CO2 and 4.476 grams of H2O. What was the empirical formula of the compound? This one's a little bit harder. So the first thing you have to know is actually what is a combustion reaction. So a combustion reaction is generally written like this. See, so you have some hydrocarbon. Why did I put a C? Something like that. I'm putting extra variables because I don't know what they are. You're combining it with oxygen, and then you get CO2 and water. Right. I'm not balancing this. It doesn't make sense to because I can't. I don't know how many carbons are on the left or hydrogens or oxygens, but this is the general form of a combustion reaction, right? You combine something with atmosphere or oxygen, and then you get CO2 and water. Both of these are gases, by the way. Um, so how do you do this? Well, the challenge with this is that you can't just look at this and say, well, all of my oxygen, all of whatever is here. Oops, where'd my thing go there? All of whatever is in these two compounds came from here, right? From my original compound. Why? Well, the first thing that makes that pretty clear is that you start with 4.5 grams, or 4.05 grams, and you end up with way more stuff in terms of mass than you started with, right? So it doesn't make sense to say that all of my carbon, hydrogens, and oxygens form everything here because of the law of conservation of mass. You can't just make stuff out of thin air. So a lot of this oxygen comes from this O2, right? So, well, what do we do now? Well, what you can say is all of the carbon in this and all of the hydrogen in this water had to come from this compound on the reactant side or whatever your hydrocarbon was, right? Because there's no other carbons or hydrogens in the reaction. There's nothing else that it could come from. So what you can do is figure out how much carbon was in here, how much hydrogen is in here. Then what we're going to do is take those away from this 4.05, as you'll see, because if I know how much carbon was from the original compound, right? It's whatever carbon is in here. I know how much hydrogen is in here, right? However much hydrogen is in here. Then I know how much carbon and hydrogen was in the original compound, and whatever was left had to be oxygen. It couldn't be anything else, right? Because it's made of carbon, hydrogen, and oxygen. So first thing we do is we start off by converting these. So for every 10.942 grams of CO2, so this really is kind of going backwards from percent composition. So you first have to find the percent composition, I guess you could say. You don't have to. I think there's an easier way to do it. But the way you can do it is like this. You're converting, you're using percent composition, right, to figure out how much carbon you have. So if it was, just throwing a number out here, if it was 70% carbon, you would do 10.942 times 0.7, right? If it was 50%, you do 0.50 times this, right? And then how did we find that out before? Whatever the percent composition was, we figured it out by taking the contribution due to some element divided by the total. So in this case, this is going to be divided by or times 12. Carbon has 12 grams per mole. And then CO2 is 44 grams per mole. And you'll notice these units cancel out, right? Because we're just doing it in terms of the molar mass of the elements, not really relating them to something else. We're just comparing how big they are to one another, which is why I didn't put grams of moles of carbon and grams per mole of, CO2. So these units cancel out. Then you can go ahead and plug this into the calculator. You get 2.98 grams. Now keep in mind, this is grams of carbon. So yeah. Actually, another way we can write this to make this make more sense is grams of carbon per grams of CO2. Again, you can do this because molar mass is related to mass, right? So if you have 12 molar mass divided by 44, it's the same ratio as 12 grams divided by 44. They are related to one another, and linear related to one another. So you can just do that. So you get this many grams of carbon. We do the same for hydrogen with the water. 4.476 grams of water for every 18 grams of water. So 1 mole of water. I have 2 grams of hydrogen. You could take whatever ratio you want. So you could say out of 100 grams of water, it's just easiest to use whatever the actual weight is. And then or mass, sorry, not weight. Let's see, we get 4.476 divided by 9, which is 0.0 by 0 grams of hydrogen. Then we can add these up. We get 3.48 grams. So what does this mean? This is 3.48 grams out of 4.05. So the rest has to be from oxygen. Right? And that's due to the law of conservation of mass. So we get 4.05 minus 3.48. And we get 0.57 grams of oxygen. And now we're almost done. Now we get to do the empirical formula thing that we did on the previous page. So, yeah, just the same exact procedure. 2.89 grams of carbon, 0.5 grams of hydrogen, 0.57 grams of oxygen. You convert these to moles first. 2.98 divided by 12, 0.248 moles. Let's just go 5. Make my life easy. Moles of carbon. For hydrogen, 0.5 moles. For oxygen, this is 0.04 moles. You divide by the smallest one, which is oxygen. So that way we can get a nice ratio. 1 mole of oxygen. 0.5 divided by 0.4. Oops. 0.04. This is where rounding kind of hurts. So I shouldn't have actually rounded the hydrogen because you get 12.5, which makes it really unclear. It's 14. So let me actually rewrite. Sorry, I shouldn't have rounded the oxygen. So 0.36. So that's one example where you do want to actually keep some extra numbers. And then carbon is going to be half of that. So the empirical formula is C7H14. So then you're done. All right, number 17. It says balance the following equations. So the way I recommend you do this is when you're balancing an equation, generally you don't know how to balance it at first. You're going to just kind of put random things in random spots until things work out. It's part of learning how you do it. Some general rules is leave this for last. So any element by itself, leave it alone. Leave it alone until you're at the end. It'll make it easy because you can freely kind of change the coefficient without changing any other elements or amounts of other elements. So leave elements last. Always leave these last. And balance everything else. So on the left side, we have P2H4. On the right, we have PH3. Now we need to balance the hydrogens. The phosphorus we'll worry about last because we have elemental phosphorus here. But let's balance the hydrogens at least right now. So, and the reason why is if you make this a 2, then it's like, well, there's a 2 here, but there's a 4 here, and then you're not going to know what to do. So I also recommend balancing the things that there's the least of, I guess, between different compounds. So that you can see hydrogen's only in 2 compounds here, right? One on the left, one on the right. Phosphorus is in 3. So leave phosphorus for later, it will sort itself out eventually. So, all right. So balance the hydrogens because it's only in two compounds versus three, makes it easier, and you have elemental phosphorus, which you want to leave for last. So balance the hydrogens. Well, the least common multiple of 3 and 4 to balance this out is 12. So I have to have 3 on the left and 4 there. You do want to use whole integers unless you are messing around with an element, which I think we may actually see here. But use whole integers for your coefficients. If you get a fraction, which is okay, so if you're balancing like a combustion reaction, and you get, say, like 1/2 for the O2, multiply everything by 2 to remove the fraction, because you can't have half of an O2. That doesn't make sense. All right, so now we balance the phosphorus, phosphori, I don't know. But there's 6 on the left. There is, oh, here's the good example of that. So there's 6 on the left. There are currently 4 on the right from pH 3. And if I put a 1 here, there's 4 here. So there's 8. So let's think about it differently. There's 6 on the left. There's 4 here. I need 2 more phosphorus, right? So if I need 2 more, I can take 1/2 of 4. Now, what I just said is you're not supposed to have fractions, right? So what you do is you take this whole thing and multiply everything by 2, just like you would in math. If you multiply both sides of the equation by 2, you get the same thing. So if I multiply everything by 2, then the fraction goes away, and it's still balanced. Done. So that is the easiest way to do it. Leave your elemental things for last, use a fraction if you need to, and then multiply both sides to get rid of the fraction if you had to use one. All right, B, it says you have magnesium nitrate, water, and then you get that stuff. So you can see here, H is in multiple things, right? You have H here, here, and here. That's too annoying to work with. So I'm not going to do H right now, right? Leave that for later. It should sort itself out. We have oxygen in one spot in both places, so that's good. We have nitrogen in one spot in both places, so that's good. And same with magnesium. So let's balance everything else. Arbitrarily, I'm going to start with nitrogen. There's no specific reason for this. So you can start with wherever you want. I'm going to start with nitrogen here. I need 2 on the right because if this is 1, I have 2 on the left. Great. Now I have 3 magnesiums on the left, so I need 3 magnesiums on the right. That's balanced. Well, now I have 6 oxygens on the right. 1 oxygen, there's 2, then multiplied by 3, right? So 2 hydroxides per molecule, or 2 oxygens per molecule. There's 3 of them, so there's 6, which means I need to have 6 waters on the left. And then this problem's done. So we actually didn't even have to do anything weird. All right, letter C. We have KMNO4 plus all this other stuff, and then it yields a whole bunch of stuff, right? So if we look at this, potassium in those 2 spots, we have potassium over there. So potassium is going to be too hard to do by itself. I think this is actually one where you may even have to set up a system of equations. I don't think anything you will get will be this comprehensive, quite honestly. So, because let's look at the other things. There's SO4. We can balance the SO4s. No, we can't because there's 3 of them. Then if you look at hydrogens, okay, maybe we can just do with the hydrogens. Let's stick with the hydrogens. Let's see where that goes. So hydrogens in one spot, iodines in one spot. So the way I solved this last year was I set up like a whole bunch of equations and it took forever. So let's use the method that I just said a few minutes ago, which is leave all the stuff that's in multiple spots for last. Hopefully it'll sort itself out, hopefully. So suppose we have one of each, right? If we have one of each, the hydrogens balance out, right? Because I have 2 hydrogens on the left, and then I have 2 hydrogens on the right. Then we can look at the iodine. So the iodine, suppose I have one I2, then I have two on the right and two on the left from the 2Ki. Now we get to do everything else, right? So what do you do? Well, let's balance the manganese. So the manganese would be the easiest one to do next because it's in one spot. So suppose I have one manganese on the left and one on the right. I don't think this is going to work out. Um, and then let's try balancing the sulfates. No, yeah, because in this ends up being this ends up being zero. Um, but that does not work. So you do have to set up a system of equations. Okay. So I will edit this out. Hopefully I don't forget. That'd be embarrassing. I'm going to edit this out. So this problem is going to be much more difficult than it looks. I will just give out the answer here. And then the answer I will post in the answer key. I don't think anything you'll have will be this difficult, to be honest. But I will show you the method that I use to solve it, which is basically setting up a whole bunch of equations. And it's not super fun. But that's the only way I can really think of solving this systematically. Moving on to the next one, we have 18 right balanced equations based on the information given. We have combination reaction, solid magnesium, nitrogen gas, it's a solid product. Oh, okay. So they just want you to write it. So you have magnesium plus nitrogen. Nitrogen is a diatomic gas. That's something you're going to want to memorize. And that gives you some solid product. I assume it would be something with magnesium and nitrogen, right? Now to balance the charges, magnesium typically has a +2. Actually, always has a +2. Nitrogen is typically a -3. So we need 3 magnesiums and 2 nitrogens. And then we can balance it on the left side, and then we're done. All right, going on to B, it's a double replacement reaction. You have aqueous sodium hydroxide plus aqueous hydrochloric acid. So sodium hydroxide plus HCl gives a liquid product, an aqueous product. So if you have an acid and a base, a strong acid and a base, strong base, for this example, strong acid and strong base, you always get water as a product because you combine the H and the OH. So doing a double replacement, you're switching the spots, right, of things. So H switches with Na, so you get HOH and NaCl, which is the salt or the aqueous product. And HOH is H2O, right? Just different way of writing it. NaCl is aqueous because it dissolves in water, and that's it. 19 says, which of the following is not diatomic under standard conditions? H2, C2, F2, Cl2, or N2. So in general, all of the halogens are diatomic. So F2, Cl2, Br2, I2. Nitrogen and oxygen are diatomic, so N2. Hydrogen is also usually diatomic, so H2. So it's usually the things that are gases, or close to being gases. So I'm not sure if fluorine is actually a gas at room temp. I think it is. Is it? I'm not sure. I think fluorine is gas at room temp. The answer is carbon. Carbon is not diatomic. Carbon also needs 4 bonds. So uh, carbon C2 can only have a max 3 if you have a triple bond. Quadruple bonds do not exist. Maybe they do. Maybe I shouldn't say that. Not to my knowledge. 20, it says for the following simultaneous reactions, write the A overall reaction. Starts with 2 moles of manganese, 4 oxide to produce manganese, 3 oxide. List the intermediates and then C indicate the correct multiplier for each simultaneous reaction. Note all manganese compounds are solids. Okay. So um, this one is quite long. It's kind of like I don't think you have learned Hess's law at this point, but it's similar to Hess's law for like enthalpy and stuff like that, but you haven't learned about that. So how do you do this one? Well, first you want to start with MnO2 from what they tell you. So we're starting with 2 moles of this reaction, right? So I start with 2 MnO2. Okay. Eventually, I want Mn2O3 for manganese 3 oxide. How much? I don't know what the coefficient is, but I eventually want that. So what do you do? So the first thing is, and the thing that is clear is that if you want to use 2 moles of MnO2, is you're going to need at least 2 moles of the first reaction. So that's plus 2 CO. I'm not writing the phases. It's going to take too long. I don't want to do that. 2 MnO plus CO2. Great. Now I eventually want this on my product side. So what do I do? You're allowed to reverse this reaction. Why? It's not really clear for you right now. But you'll see in the future, if you're trying to add reactions and get an overall reaction, whether it's Hess's law or looking at net reactions like this, you can reverse reactions. So if I reverse this reaction, I'm just going to switch the product side things and that 2Mn3O4 plus CO2 yields 3M Mn2O3 plus CO. Now, if I were to add these reactions, which is also what you're allowed to do, think of it like mathematics. You're allowed to add equations together, right? Probably took the SAT or ACT, or some form of algebra, I assume. Um, you can solve by elimination, where you add 2 different equations together. You eliminate one. In this case, we're not eliminating anything, but we are allowed to add reactions together, right? So if I add these things together, I will get 3MnO2 on the right and this on the left. Now, there's a whole bunch of other stuff that I don't really like being there, right? Because I'm going to get MnO2 on the left. I'm also going to have this M3O4, which is not mentioned for the overall reaction. Um, and then I have this other random MnO sitting here. So what do I do to get rid of this stuff? Well, what I can do is use the second reaction. So the second reaction, I have Mn3O4 plus CO gives me that stuff. So if I add the second reaction, things are going to cancel out. Why they cancel out, I'll show you. But take my word for it for a second. So I'm going to reverse this reaction. When you have things on opposite sides of the arrow, so if I told you NaCl turns into NaCl, that basically tells you nothing happened, right? So if you have things on opposite sides of the arrow in 2 different things that you're adding for 2 different equations, you can cancel them out like that. So I want to get rid of all this other stuff that's not the thing I want, which is 2m and O2 to start with, and the thing to end with, which is 3m and 2O3. So for the second equation, I have to reverse it, right? I need this m and O3, m and 3O4 to cancel out with this one from the third reaction. So I need to reverse it. I need it to be on the right side of the arrow so I can eventually cancel it. And I need two of them. So I'm also going to need to multiply this whole thing by 2. So 2mn3O4 plus 2CO. Then on the right side, which is now on the left because I reversed it, there's 6MnO because I multiplied by 2 plus 2CO2. Now all I have to do is cancel out the things that can cancel out. So this cancels out as desired, right? Because they're on opposite sides of the reactions and we're adding all these up. The MnO does not fully cancel out. So we still have 4 on the left. Oh, yeah, no. We still have 4 on the left, which I guess is fine. Actually, do we want to get rid of it? Let's get rid of it. So if we want to get rid of it, we're also going to multiply this whole thing. Because we just want the one thing we're starting with, right? This 2MnO2. So let's get rid of it. It doesn't really make sense to have 2 manganese things as your reactants, right? You're not going to add multiple things. You just want to add one thing and then have your reaction done. So to get rid of the 2MnO, we have 6 in the second equation, which means we need 6 in the first one. So this ends up being 6 if you multiply it by 3. So now let's go ahead and start canceling things. So 2m3O4 cancels out. These MnOs cancel out because they're 6 once you multiply it out. Then there's 2 COs, except there's 4 more on the top, remember, because I didn't multiply it out. So now there's 3 COs on the left. And then for CO2s, there's 3 on top and there's 3 there. So there's no more CO2s. So overall, my net reaction should be, when you cancel everything out and multiply it all, 6MnO2 plus, I believe it's 3 CO is what I said, right? Yields 3MnO3. And then, did I cancel out the CO2s correctly? That was 1, 2, both were reversed. That's 3. Yeah, that should be correct. No, wait, because then the COs are not balanced. Give me 1 second, sorry. The mistake I made is I forgot to, when I first multiplied the top by 2, way in the beginning, I forgot to do that to the carbon dioxide as well. So then I get 3 CO2 here. Now all these share a coefficient of 3, so you can divide everything by 3. So I guess I did some unnecessary step somewhere that I'm not seeing. But divide everything by 3. Then we get 2MnO2 plus CO yields MnO3 plus CO2. And that is your overall reaction. All right, then B, what are the intermediates? So what are the things that are formed and then go away? So you can see that MnO is formed and then it goes away in the second one. Same with M3O4, it forms in the second one and then it goes away. So MnO and MN3O4. And then for C, it says indicate the correct multiplier for each reaction. So I did 3 and then 2 and I reversed it. So you can say -2, that would be the multiplier. And then the last one I left the same, but I reversed it, so -1. So if you reverse it, you can consider the multiplier as a negative, which will be important later on. Right now, it's like, well, why does that make sense? Why does that even help? When you get to Hess's law, it will make sense. 21 says, how many moles of NO can be produced in this reaction of 3.00 moles of NH3 and 4 moles of O2 gas? The reaction is not balanced. All right, so the first thing we want to do is balance the reaction. So suppose I have my 1 nitrogen on each side like that to make it easier to balance. Then I need 3 halves for the water. So that way, again, I balance the hydrogens. If you don't trust me, 3 halves, you can multiply it out, right? So 3 halves times 2 hydrogens gives you 3. So I have 3 on the right, 3 on the left. I'll get rid of the fraction later. On the right, I have 1 oxygen plus 3 halves oxygen. So I have 5 halves oxygen on the right. So I need 5 halves on the left. So should be 5/4. If you don't trust me, again, multiply it out. 5/4 times 2 is 5/2. So now everything is balanced. Now we don't want the fractions, so I'm going to go ahead and multiply everything by 4. So that's now 4 instead of 1. 4 is the biggest denominator, which is y. That's 5. That's 4. Then this is 6. And now it's balanced. How many moles of NO can be produced in the reaction? Have NH3 gas and 4 moles of gas. So this is a limiting reagent problem. Now, how do you do this? So the first thing you want to do is figure out which one is the limiting reagent. So bear with me. I'm going to talk about it. If you already understand it and you just want to see the answer, go ahead and skip. But I'm going to talk for probably about a few minutes. If you have a recipe, this analogy does work, trust me. If you have a recipe, let's say you need 2 eggs and 1 cup of flour, and that gives you 1 loaf of bread. I don't know how to bake bread, so maybe it's a really bad loaf of bread, but let's suppose that's the recipe. Okay, so 2 eggs, 1 flour, you get bread. There's no yeast apparently. All right, so if I told you that was the recipe and I said you were given 2 eggs and 2 cups of flour, which is limiting? Well, immediately a lot of you would say, well, that's obvious. Obviously, it's the eggs because I need 2 eggs for 1 recipe, right? And I only have 1 cup of flour. So, and that's right? You can only, the eggs are limiting because you have the same amount of both, but it takes more eggs per recipe than it does for flour. So let's put this into math because that's what we're going to have to do for the limiting reagent problems. So instead, a way you can look at this, and it's equivalent, right? But another way to look at this and the way that's going to help you for these limiting reactant problems is look at how many times you get to make the recipe, right? So if I have 2 eggs, for every 2 eggs, I can make the recipe 1 time. right? So overall, from the eggs, I get to make this recipe once. That is how many times I get to make the recipe, right? Great. Now going down to flour, let's do the same thing. So for 2 cups of flour, it'll make sense. I promise this will make sense as to why I'm doing this with limiting reagent. So 2 cups of flour, I'll just do FL, is what we start with. And then for every one recipe, it only costs me 1 cup of flour. So overall, I get to make 2 recipes, right? And then what you're doing is you're choosing the one that you get to make less recipes with. That is the one that is limiting, right? You get to make the recipe once with your eggs. You get to make it twice with your flour. Obviously, you can't pull eggs out of thin air. So you get to make the recipe once, right? So the eggs are the limiting ingredient. Or in our case, we'll be using limiting reactants, right? So going back to our problem here, right? And if I change the problem here, right? If I told you, let's say instead, I said you had if I told you you had 5 eggs and 2 cups of flour, you would do the same thing. I just really want to drive this point home, how you're doing this limiting reactant stuff, because it also seems to be a big point of confusion for students. You're not going to look at which moles are smaller. You have to look at which moles are smaller relative to how much is being used when we look at the problem. Just like with this, right? We're using more eggs. So you have to consider that you're using 2 eggs and not 1. So what about 5 eggs and 2 cups of flour? Well, every recipe costs me 2 eggs. So if you, oops, I start with 5 eggs. If you do the math, you get to make this recipe 2.5 times. For the cups of flour, it's 1 cup of flour for every one recipe. You get to make the recipe 2 times. Now, the flour is the limiting thing because you can only make the recipe twice with how much flour you have versus the eggs. So you have to keep in mind with how much you're using, right? Another one, very easy one. If I told you that you had, let's say, give me 1 sec to think of one. So let's say your recipe instead now, so it's the same recipe, 2 eggs, 1 cup of flour. But instead, let's say you have 2 eggs and 1.5 cups of flour. If you do the math there, you can make the recipe once with 2 eggs and 1.5 times with your cups of flour. So just because you have more eggs does not mean you get to make the recipe more times, right? So this relates, and hopefully that helps, the limiting reactants, and I'll show you how it relates. So it says, how many moles of NO can be produced in this, given these things? Well, consider the balanced chemical reaction as your base recipe. That is the recipe you're going off of. That's the recipe you're looking at. That's the recipe you're going to do your math on. But that's what you're comparing it to, okay? Great. So I have these 2 ingredients. I have 3 moles of NH3 and 4 moles of oxygen, right? Moles, again, are just a count of something. So it's the same as thinking 2 eggs or 1 cup of flour. It's just a measurement. It's how much of something. So do make sure you're doing this in moles, not grams. But your mole is a measurement of how much you have, right? This equation you can think of in terms of atoms or molecules or in terms of moles, right? Because again, they're related. If this happens for every 4 atoms of NH3 and 5 atoms or molecules of oxygen and 4 molecules of NO, and you get 6 molecules of water, it's the same idea if you multiply everything by 6.022 times 10 to the 24th. You would have 4 times 6.022 times 10 to the 24th NH3s, with 5 times 6.022, right? It's the same thing, right? So you can think of this in terms of moles instead of just atoms. They're just measurements of how much of something there is. So if you think of this in terms of moles, our unit of measurement, let's see how many times I can do this reaction or this recipe with the things I am given. So if I have 3 moles of NH3, right? I have 3 moles of NH3. It takes me 4 moles of NH3 to do this reaction 1 mole times to get 1 mole recipes or reactions, right? 4 atoms for 1 reaction. So 4 moles of atoms for 1 mole of reaction. Yeah, and it's just a unit of measurement. It's just how many times. It's just a counting unit of measurement. This is 4 moles of NH3. That's what the coefficients mean. They're telling you how many moles or how many molecules you have in the reaction per reaction for every 1 mole of reaction. And you get 0.75, right? And you notice the units cancel, right? Then we do the same for oxygen. So for oxygen, you start with 4 moles of oxygen. Then you have 1 mole of reaction. So I want to see how much I'm going to get. For every 1 mole of reaction, it's going to cost me 5 moles of oxygen. So given how much oxygen I have, I can do 0.8 moles of reaction. Again, think about it in terms of the recipe. I promise it'll make it easier to conceptualize. So I can only do this reaction 0.75 mole times or make the recipe 0.75 times with NH3 versus 0.8 with oxygen. So NH3 is limiting because you can do it less times, right? Now we're not done yet because we still have the last part. So it says how many moles of NO can be produced. So we found out which one is limiting. And instead of it, let's make this reaction. So instead of, so now we figure out what's limiting. Now we just have to do the same with NO. So again, think about the recipe. So in the recipe example, every recipe gave me 1 loaf of bread, right? In this case, every time I do the reaction, I get 4 moles of NO. Oops. Right? Now, how many moles of reaction? I shouldn't have put 1 there. I have 0.75 because that's the most I can do, right? It's the limiting, NH3 is a limiting reactant, and I can do this reaction 0.7 mole times. Then you plug that in, you get an answer. So you get 3. And then you're done, right? Another way you could look at this is once you find the limiting reagent, notice how these are the same coefficient. So you're going to get the same moles going in and coming out if they're the same coefficient, and it's the limiting one. All right. So we have these ones next. It says silicon carbide is on the hardest substances known, making it valuable as an abrasive. It is made by the high temperature reaction of silicon dioxide with carbon. Determine the limiting reagent when a mixture of 5.00 times 10 to the third grams of silicon dioxide and 5.00 times 10 to the 3 grams of carbon react. What is the maximum number of grams of silicon carbide that can form? So again, this is just a limiting reagent. So same thing. First, we have to, let's see, is it balanced? No, it's not. So the oxygens are not balanced. There should be a 2 there. then the carbons are not balanced. There should be a 2 there. So double checking, 1 silicon on both sides, 2 oxygens on both sides, 2 carbons on the left. Oh, now there's 3 on the right. So that should actually be 3. Good. Good thing we double checked. So that should be balanced now. Um, so same thing. Same thing. First, again, you have to convert to moles, right, of each of these. So I'm going to do it all in one step. So first, I'm going to convert 5.00 times 10 to the third grams of silicon dioxide to moles. So then I can figure out how many moles of reaction I can get out of silicon dioxide. Yeah. So, sorry, hand sweaty. So first we convert to moles. Silicon dioxide has a molar mass 60.08. So now I have the moles. Now I can figure out how many moles of reaction I get. Well, if you look at the balanced chemical equation, make sure it's balanced. For every 1 mole of silicon dioxide, I get to do this reaction once. So when you plug this all in, you get 83.22 moles of reaction. Then we're going to do the same for, whoa, there, for carbon. So 5 times 10 to the third grams of carbon. And again, notice how the masses are the same, right? But you can't figure it out based off of the masses because you have to go based off of the moles. And then these have different coefficients too. So you have to do this every time. You can't just look at it and say, I know that's going to be less, right? An egg probably weighs, I mean, maybe it's about the same as a cup of flour, but let's say if it called for 3 cups of flour for a recipe, right? An egg weighs much less, but you still need more flour, right? Um, so on and so forth, right? There's a whole bunch of analogies you can make, but you can't visually inspect it. You have to do this. So first we convert to moles. Again, there's 12 grams per 1 mole for carbon. Then for the reaction, you get 1 reaction coming out, 1 mole of reaction for every 3 moles of carbon. This is why it's important to balance, and that's why it's a good thing we checked it before. Then you get something. So 5e to the third divided by 12 divided by 3, which is 138.89. So clearly the SiO2 is limiting. So SiO2 produces less reactions. So now we can calculate whatever we want. So we know SiO2 is limiting. Now it says, what is the maximum number of grams of silicon carbide? Out of space. So I have 83.22 moles of reaction that are going to occur, theoretically. For every reaction, I get 1 mole of silicon carbide, or one for every 1 mole of reaction, get 1 mole of silicon carbide. And then the molar mass of silicon carbide is 40.11. If we want to go to grams, we don't want to stay in moles. And then you get your final answer of 3.34 times 10 to the third grams of silicon carbide. Then it says, what is the maximum number of grams of, oh, wait, no. B, how many grams of the excess reactant remain after the reaction is completed? Um, I will let you figure that one out because I'm out of room, but I'll tell you how to do it. Um, so because I'm out of room, I'm not going to do it, but I'll say it in this video. So if you've gotten to this point, the way you do this is you know how many moles of reaction actually happen. You know how many could have happened with the oxygen. So going back to the recipe analogy, the recipe takes 2 eggs and 1 cup of flour, uh, and you have 2 eggs and 2 cups of flour. You use up 1 cup of flour, right? Because you can only make the recipe once. So you take the difference of these, and then you go back. So that's your moles of reaction. And then you go back to grams of carbon. So then you go from moles of reaction that are left over to grams of carbon, which is, you just multiply it by 3. Or, whoa, moles of reaction to grams of carbon. So yeah, you would multiply by 3 to get the moles of carbon left over. And then you would, um, yeah, then you would multiply by the molar mass uh, to get the mass. Then 23, it says the reaction below is 0.20 moles of N2 and 0.90 moles of H2. How many moles of H2 gas will be left unreacted after the reaction has gone to completion? Yeah, so there's no point in doing the other one because we're going to see it here. Okay, so this is not balanced either. So if I were to add a 3/2 there, it would be balanced. No, it's still not balanced. If I add a 3/2 there and a 1/2 there, it's balanced. So if I multiply everything by 2, we get a 1, a 3, and a 2, and now it's balanced. Um, all right. So doing the same thing. First, you can figure out which one is limiting. So for N2, you start with 0.2 moles. You're going to get 1 mole of reaction for every 1 mole of N2 you use because the coefficient is 1. So you end up with 0.2 moles of reaction. Great. Then for H2, you're going to do the same thing. You start with 0.9 moles. For every 1 mole of reaction, you're going to use up 3 moles of H2. So you get 0.3 moles of reaction. Therefore, N2 is limiting because you can make less moles of reaction. Then we go ahead and say, well, we have 0.3 minus 0.2, which is 0.1 moles of reaction, right? And then again, you have to interpret your answer. So this is that hydrogen could do, but there's not enough nitrogen, right? Because it's limiting. And then we just go backwards. So 0.1 moles of reaction. There are, for every 1 mole of reaction, you get 3 moles of hydrogen. And then you get 0.3 moles of hydrogen. All right. All right. We're almost done. So last one. It says if the percent yield is 82%, how many grams of silicon is needed to make 105 grams of chromium by the reaction of that? All right. So you know what the percent yield is. Okay. that makes sense. So your percent yield is your actual yield divided by your theoretical yield, right? So if you want to make 105 grams of chromium 1, you're going to have to compensate with a less than 100% yield. So if you want to make 105 grams of chromium, you must prepare to make 105 divided by 0.82. You can get that from the percent yield formula. So actual divided by theoretical. You must prepare to make 128.05 grams, right? That's your theoretical yield. So, and again, it's because your yield is less than 100, so you have to prepare to make more, right? If you want that much. And then it's just, you're just going backwards here. So it says, this is now stoichiometry. So first we go ahead and convert this to moles of chromium. I don't know how much chromium weighs or mass of it. You can stop saying that. 51.9961 grams for 1 mole. Then I want to compare these things. So before we were going to moles of reaction because that was the easiest way to find the limiting reactant. But you don't have to, right? Assuming that you are actually doing the reaction, you can directly compare these things, right? So in the recipe, again, think about a recipe. Example, 2 eggs gave you 1 loaf. So if you had 4 eggs, you could say 4 eggs. And then every time I use 2 eggs, I get 1 loaf, right? And then you get, I make 2 loaves, right? So I didn't have to go through moles of reaction. That just makes it easy to do the limiting reactant stuff. If you don't have to, then I wouldn't do it. I would just skip to doing whatever's on the product side or reactant, whatever you're solving for. Similarly, you can go backwards. If you want 4 loaves of bread, you need 8 eggs, right? So either way around works. So for 1 mole of chromium, so I have moles of chromium now. Then for every 4 moles of chromium, I want to check how many grams of silicon I need. So I need to go to moles of silicon. So for every 4 moles of chromium that's produced in this reaction, I have to use 3 moles of silicon. And then we can go from moles of silicon to grams. 28.09. For every 1 mole of silicon. And again, this is where you do want to keep track of your units. And then you plug this all in to get 51.9 grams of silicon. And then we're done. All right. So I hope that helps. Yeah, so I hope that helps. See you in the next video. And enjoy the week.